Okay, we're back. Time to get back into Rust. So, in this video, we're going to cover control flow. If you're new to this video series, we are reading through the Rust programming language book. It's one of the canonical resources for learning Rust. So let's do it. Let's keep going. We got control flow, which is here described as the ability to run some code depending on whether a condition is true, and the ability to run some code repeatedly while a condition is true are basic building blocks of most programming languages. Yeah, I mean, this is actually very old. I couldn't give you a year for when it started, but this is called structural or structured programming or something like that, which is not just using structs or structures. It is also having like loops instead of go-to statements, for example. Yeah, anyway, I don't know what to even say about this other than that it's so fundamental to computer programming that some version of control flow is beyond my imagining for how you would make a computer work. You need branching behavior in one way or another, whether it has to be strictly in terms of an explicit Boolean type or not. So with that thought, let's move on. The most common constructs that let you control the flow of execution of Rust code are if expressions and loops. So that's kind of a fun tidbit already, which I didn't specifically know about Rust, but it kind of makes sense. It's definitely true of Python that many things, including loops, that might at first glance look like they're not branch points in the program, are. Even for loops have at least one branch point. And so when you're thinking about the flow of information in your program and thinking about all the different things that you might want to test or at least consider testing, even where your loops occur, not just where your if, else, and your case matching and stuff like that occur, it's also where your loops are. So that's food for thought. Create a new project called branches in your projects directory to explore the if expression in the source main RS file. Input the following. So, okay, let's go cargo new, and we'll call this branches as they do, and we'll go into branches. And we will open up that source code, and here we've just got a print hello world script by default, but we can copy out what they've got there. We can say number is bound to 3, and then we'll go if number is strictly less than 5, then we'll enter into this block. And under this case, we'll use the print line macro, that's the bang. Condition was true. I mean, we're setting the bar pretty low here for what we're going to get out of our computer program output, but that is perfectly all right. We're here to learn. So we've got else. So if it's not the case that it's strictly less than 5, which would mean that it's 5 or greater for an integer, being compared using the strictly less than, of course, I'm kind of dancing around, well, you know, there's other things you could compare, and you can have operator overloading. But let's not get into that. Let's just get into condition was false. Great. And then if we go cargo run, condition was true. Why? Because we set that number was 3, and 3 is, in fact, less than 5. So, you know, it's kind of a silly program from the perspective of something you would want in production, because of course you can just check that this is obviously true without using a computer program. But that's not really why we're looking at examples like this. It's to see, if you're just unfamiliar with the Rust syntax, it's to see the syntax and go, oh, okay, that's all that an if-else block looks like. And if you're new to programming and Rust is like your first programming language, then this is also your first opportunity to see really obvious behavior, which helps you map the semantic idea of control flow to the syntax. Okay, so all if expressions start with the word if. Oddly enough, it's a very apt name, followed by a condition. That is, a condition in this context of programming is some expression that has to evaluate to a Boolean. In this case, the condition checks whether or not the variable number has a value less than 5. Now I'm thinking to myself, like, if I have something that evaluates to a Boolean, but it doesn't actually go into an if block or a while or anything like that, I wonder if that still counts as a condition. I mean, that's not usually what people would say, so maybe not. Let me know your thoughts in the comments. We place the block of code to execute if the condition is true. immediately after the condition inside the curly brackets. That is, we're looking at this. Blocks of code associated with conditions in if expressions are sometimes called arms, just like the arms in match expressions, as we discussed in comparing the guess to the secret number section of chapter 2. So that was kind of a cool example because it was our first kind of, I wouldn't want to say that it was a practical or production ready kind of thing, but there were at least multiple concepts going on. I think programming a guessing game is a good starter, especially if you're already familiar with computer programming, and what you really want to see is just some basic coding example in the terminal that includes multiple features, including crates and control flow and user input and blah, blah, blah. All right. So optionally, we can also include an else expression, which we chose to do here to give the program an alternative block of code to execute, should the condition evaluate to false. If you don't provide an else expression and the condition is false, the program will just skip the if block and move on to the next bit of code. Yeah, so we should be able to outright delete this, and then if we run it, we'll still get condition was true. Yes, there's a bunch of red output here, but it's not really errors. It's just, I don't know. It's just whatever the logger has decided to put it as in NeoVim. All right. Let's put that back, though. All right, so try running this code. We did. We get condition was true. Let's try changing the value of number to a value that makes the condition false to see what happens. So we should be able to make a prediction at this point that it will print condition was false, because if we set this to any number that's greater than or equal to 5, then it should go down this else branch, because it's the remaining alternative after considering if number was strictly less than 5. So let's give it a go. This time, actually, let's put a terminal down here. And cargo run, and condition was false. There we go. That's what we predicted based on simple inequalities between positive integers, which, if you remember from discussing types, I think we've discussed types, basic types, is that by default this is like a U32, I believe it is, for a default integer. Okay, what is next? It's also worth noting that the condition in this code must be a Boolean. If the condition isn't a bool, we'll get an error. For example, try running the following code. So if we tried to set this, oh, I see. So in some programming languages like Python, there's not only Boolean values, there's also what are called truthy values, which is a way of automatically converting certain data structures into Boolean expression, into bools, into true-false values. Usually things like with Python lists, if I was writing in Python, I guess we could literally write in Python for a sec, if empty list, print I am not here. And this is valid code, but it doesn't actually print because the truthy value of an empty list is false. If I put an A or something like that in there, and then print, oops, I've got a little problem with my IDE here. What am I trying to do? There we go. That we get I am not here because a list that contains elements is considered true, whereas a list that is empty is considered false. Okay. Actually, I didn't want to do that. I just wanted to split, but I did want to go back to terminal. Now I've got to think an extra buffer, but that's okay. I can close it later. Okay. So let's go back to the Rust side of it. If we go cargo run, we get this error, expected a Boolean, found an integer. And this is where, while I wouldn't say that every Rust error I've come across is great, this is a reasonable error, I think, to go like the programming language says that number here has to be a Boolean and instead found an integer. And Rust does come with, and I don't know if we've covered this before, the last one of these videos that I put out was actually some months ago, and so I don't remember if we've talked about this, but you can look up errors using this lookup. It'll give you a basic description, and there's a ton of resources online that explain especially really common errors. Okay, so we could fix this by setting this back to comparing an integer with an integer to create a Boolean. Let's see what their next example is. Oh, they're going to explain the error to us. So the error indicates that Rust expected a Boolean, but got an integer. Unlike languages such as Ruby and JavaScript, Rust will not automatically try to convert non-Boolean types to a Boolean. You must be explicit and always provide if with a Boolean as its condition. If we want the if code block to run only when a number is not equal to 0, for example, we can change the if expression to the following. So their example, they just say like not equal to 0. And if we run that, we get condition was equal to true because 3 is not equal to 0. And just so that we finally go down this other branch, you could see condition. Did I not save? Oh, that's perplexing. If we let the number equal 0, and then if it's, no, I'm just being silly with not remembering basic logic. All right. Because then if we go this way, then the condition was true. Good, good, good. The world does work the way that I expected it to. All right, so we've got this example. We just ran it, although we did use a different print statement, maybe just for the sake of matching what they've shown. Let's go. Number was something other than 0. Close that if statement off. And we don't see a printout because 0 actually is equal to 0 because I changed the example on us. All right, let's go back to the original example so that we can see it the way that they intended us to see it. Number was something other than 0. All right. So they say running this code will print number was something other than 0, which is what we say after we fix the changes that I made to the example, oddly enough. All right. Handling multiple conditions with else if. You can use multiple conditions by combining if and else in an else if expression, for example. And they've got this little example we can set up here. So let's follow along. The first thing they do is they set up that there's this defined number. And then they've got multiple, what do they call them, arms? I keep wanting to say clauses, but they're arms. Percent. For, and if number is, by the way, the percent here is modulus, so like it's a remainder function. So if number modulo 4 is, and we need to specify equal to 0 because we don't have truthiness here, we have only truth. If number modulo 4 is equal to 0, then we'll print this message: number is divisible by 4, meaning there's a remainder of 0. So number divides by 4 evenly. Now we can add more clauses. So before we only had if and then else, but we can continue to expand the number of arms that we want to have in our example. So here we're going to do something very similar, modulo 3 instead of modulo 4. Now, of course, you're probably, if you're kind of an abstract thinker, looking at, you could probably generalize this code to check a sequence inside of a loop, if you're already familiar with loops. But we're not going to do that. We're going to follow along. There's our divisible by 3. But we'll do another one. If number modulo 2 is equal to 0, in other words, it's an even number, then we'll say print line macro number is divisible by 2. And then we'll add one more arm, and this is the else. So if it's not any of the above, how are we going to handle it? What are we going to implement? We're just going to print line macro number is not divisible by 4, 3, or 2. All right, let's give her a go. Cargo run. Number is divisible by 3. Does that make sense? Let's just double check our code. We've got number modulo 4 equals to 0. Makes sense why that's not true, because 6 divided by 4 has a non-zero remainder. But 6 divided by 3 does have a non-zero remainder, because 6 divided by 3 is 2, obviously. Now, notice that while 6 is divisible by 2, it is an even number, because 6 divided by 2 is 3. Why didn't this print? And it's because it's going to basically run this code in the first arm that it hits and then skip over everything else. So that's one of the things that you can put into if-else blocks, is this kind of path dependence of a decision model, which sometimes is important to watch out for, because sometimes you can refactor these for better performance by not nesting too much and putting things more into a sequence rather than nested. But sometimes you want to have some sequence of considerations. You can kind of read this as like, well, if the number modulo 4 is equal to 0, otherwise, if the previous stuff is not true, that is, that the number wasn't divisible by 4, then you move on to the next thing of saying, well, and also, is it number modulo 3 is equal to 0? No? Then you go on to the next one. You go on until you get to the else clause, if there is one. Otherwise, tacitly, I don't know what's actually in the underlying code for the compiled stuff, but you end up with something that's practically the same as if you had left else as basically empty. Okay, did we run it? Yes, we ran it already. All right, so this program has 4 possible paths it can take. After running, you should see the following output. That number is divisible by 3, and lo and behold, that is what we get. So when this program executes, it checks if each if expression in turn and executes the first body for which the condition evaluates to true. Note that even though 6, oh my goodness, I'm just like a savant at going like, what would I explain here? And then reading in the documentation the thing. I swear I've not pre-read to go, well, I actually have read big chunks of this book, but I didn't like pre-read this today to go like, I'm going to talk about the branching behavior. Maybe I should be more patient and let the book do the talking, but I just like to give my 2 cents, even if it's redundant sometimes. Ouch, that hurts. Okay, so now that even though 6 is divisible by 2, we don't see the output number is divisible by 2, nor do we see the number is not divisible by 4, 3, or 2 text from the else block. That's because Rust only executes the block for the first true condition, and once it finds one, it doesn't need to check the rest. That's a nice, concise way of saying what I was trying to say. So using too many else if expressions can clutter your code. So you can have more than one. So if you have more than one, you might want to refactor your code. Chapter 6 describes a powerful Rust branching construct called match for these cases. Okay, I mentioned match, but I think if you're reading along, we have not actually covered match. So we'll behave ourselves in sticking to the topic at hand. So is there anything else I want to add to this? I mean, I think that it's not really a matter of too many in and of itself, of like, is it cluttering your code to have else if, but rather that sometimes there's a better way, sometimes there's not. Like, you're not necessarily doing something wrong if there are 1,000 arms. I don't generally write code with that many. Like, that would be a statistical anomaly where I would be questioning, man, am I doing this right? Like, why are there so many branches? That maybe I need a loop, for example, or a lookup. Anyway, so it's something that you might want to consider as a warning sign if you have a lot of them, because in practice, if-else blocks tend not to have a huge number. But I would also say, as a caveat to that, you're not necessarily doing something wrong. So, next little subsection here, using if in a let statement, because if is an expression. That is, an expression is a statement that has semantic value and evaluates. It has a value that it turns into. Although I should be careful, I think with Rust, they not only distinguish between statements and expressions, which most languages do, but depending on the language and jargon, for some languages, all expressions are statements, but not all statements are expressions. I have a feeling, though, that Rust might just say that they're wholly distinct. We'll have to come back to that question at some point. So, because if is an expression, we can use it on the right side of a let statement to assign the outcome to a variable, as in listing 3.3-2, sorry. Yeah, so let's go to their example, and they've got let condition be bound to true, and then let number be bound to if condition. They've got 5, else 6. Now, you got to be careful with one-liners because they can be kind of, I'm going to try everything on the keyboard before I get that right. Okay, so they can be nice to do these one-liners, especially really simple stuff, but often past some point of complexity, it's easier to break it up across multiple lines. I think my Rust analyzer is going to run a formatter that basically puts that back to this. This is considered what the formatter likes, and I'm not going to fight it. So, last thing in their example, print line macro, the value of number is number. Let's see what we get. The value of number is 5. Because oddly enough, condition being true, and if condition is true, 5, else 6. Now notice, and this is the whole point of this section as far as I understand it, is pointing out to us that an if-else can be used to bind a value to a variable like this. It can be an expression. It is an expression. So contrast that to programming language like Python, where if I said condition is bound to, they use a capital T, condition true, I cannot say, like, not only is the syntax different, but even if I tried to like match it as close as I can to Python to go, well, like condition equals if condition, not condition, sorry, my bad, number is bound to the value of if condition, like it just doesn't even begin to work with the Python syntax. What you could use in Python is a ternary operator. You could go 5 if condition else 6 is probably the more conventional Python way to put it. And there's your 5. So that's food for thought. You can put more in these blocks in Rust if you like, but that is just a point of comparison. So it's not that Python doesn't have some kind of programming mechanism that looks like this, but for Rust, genuinely, your if block does a very similar thing. You can do these one-liners. Okay, so we did that example. Next thing, the number variable will be bound to a value based on the outcome of the if expression, 100%. So depending on the branch we go down, it'll change the answer. So here we got the value of 5 because condition is true, and that's what we've set it to. Now, what else? I'm tempted to quickly, I don't know, I have a bad feeling I'm just going to say something that it's about to say, but what if we set this to false? And then we ran cargo, oops, got a little bit hasty with my history there. So now it's a value of 6. Like, it really does depend on the branch that it goes down for which value gets bound to number. All right, let's take a look at what they actually wanted to say, because I'm not sure if that's what they were going for. Let's see. Remember that blocks of code evaluate to the last expression in them, and numbers by themselves are also expressions. Right. In this case, the value of the whole if expression depends on which block of code executes. This means the values that have the potential to be results from each arm of the if must be the same type. Good point. Like, I can't, actually, I was about to do the thing, but this is what the point of their example is. Let's just wait. Let's just be less impatient. This means that the values that have the potential to be results from each arm of the if must be the same type. In listing 3-2, the results of both the if arm and the else arm were i32 integers. If the integers are if the types are mismatched, as the following example, we'll get an error. So here, the thing that they've changed is they've thrown in a string literal or string slice thing 6, and now you can see there's already an error for something about incompatible type in my LSP, but we're just going to run and see what error we get. So we get if and else have incompatible types, and it's very clearly pointing out that this is compared to this, and it goes one type at a time, I guess, in order. So the first type was, a U32, and it says, well, we expected like a uint, because here, and so that's why we expected an integer, but we found, yeah, like a reference to str, reference to string literal. So not good. And that is not to say that you can't have multiple things going on. Like if I said print line foo, and then I said, notice that I'm relying on my editor to set me straight. Now, it still doesn't like it because there's an incompatible type. I don't know what println macro technically returns, because println macro is not actually Rust. It's a Rust macro that's not in Rust itself. It's a whole confusing thing, but suffice it to say, you know, if I put the 6 back in here, now it should be fine, but it will print foo. There we go. It'll print foo if I go down that branch. So it's not like you have completely bundled in to looking at only values down each branch. You can have other kinds of behavior. But because it's acting like an expression, it does need to give something, and that something needs to be consistent across all of the arms. I keep saying branches, arms. Okay. Clear as mud? Did we cover this example? That's the example. That is the example we just covered. So when we try to compile this code, we'll get an error. The if and else arms have value types that are incompatible, and Rust indicates exactly where to find the problem in the program. So we just read exactly this error. We're good with that. The expression in the if block evaluates to an integer, and the expression in the else block evaluates to a string. This won't work because variables must have a single type, and Rust needs to know definitively at compile time what the type number variable is. So that does contrast to Python with its dynamic typing, where you can kind of go like, well, I said it was going to be this type, but actually, whoops, gotcha, it's a different type. Put in the comments if you want to see an example, but I think I'll leave that one. So Rust needs to know definitively at compile time, knowing the type of number lets the compiler verify the type is valid everywhere we use number, which can be a very valuable piece of validation. And that's one of the advantages of static type analysis. So Rust wouldn't be able to do that if the type of number was only determined at runtime. The compiler would be more complex and would make fewer guarantees about the code if it had to keep track of multiple hypothetical types for any variable. There's a kind of phrase that I like to say once in a while to remind myself that what happens at runtime stays at runtime, which is not 100% true, but it is true that, especially in some programming languages that are very flexible, that it can be hard to know ahead of time what the runtime behavior actually is, and that in some programming languages, it's kind of impossible to tell. You just have to run it to find out, or do an extremely difficult analysis to find out and derive it. Okay, repetition with loops. I think I did mention that, you know, loops combined with conditionals can be very useful, and they are themselves something that can have branching. So let's take a look. It's often useful to execute a block of code more than once. For this task, Rust provides several loops, which will run through the code inside of the loop body to the end, and then start immediately back at the beginning. To experiment with loops, let's make a new project called loops. Let's quit out of that stuff, and let's go up and go cargo new loops. Let's take a look. Maybe we'll just set up as we did before. Okay, so we got this hello world, but that's not the example they want us to run. But we've made the file. Rust has 3 types of loops: loop, while, and for. I am actually kind of curious about really why I would want to use like loop versus while loop. And the only main thing I have seen so far, and maybe I'm jumping ahead, but with loop, you don't have to specify a condition. But often, not always maybe, but often you should put a break statement somewhere in there, and you can even return values kind of like an if statement. It's an expression. But let's not jump too far ahead of ourselves now. Let's get into what they want to talk about. So repeating code with loop. The loop keyword tells Rust to execute a block of code over and over again until either forever or until you explicitly tell it to stop. As an example, change the source main file in your loops directory to look like this. Okay, so we got loop, and then we'll go print line macro. This program will run forever. When we run this program, we'll see, again, printed over and over again continuously until we stop. Most terminals support the keyword shortcut Control-C to interrupt the program that is stuck in a continual loop. Give it a try. Sure, we'll give it a try. So, and it just goes on and on and on and on and on and on. Okay, so we'll go Control-C, and there it stops. Good. Let's take a look at the next thing. So that ran. Oh, I'm curious. I didn't get the magical again of the control again. I just got again. Maybe that's because I'm inside of NeoVim. Okay, so anyway, the symbol *C represents where you pressed Control-C. I have a feeling like if I had done this in just raw bash, I would have gotten that symbol printed, but that's okay. You may or may not see the word again printed after the Control-C, depending on where the code was in the loop where when it received the interrupt signal. Good to know. So that's not like a particularly informative piece of information of whether the last printout is before or after, but it does technically tell you where relative to that last execution, I guess. Fortunately, Rust also provides a way to break out of loops using code. Yeah. I mean, I don't really want to imagine a world where that wasn't true, so I'm quite glad that somebody has implemented that for Rust. You can place the break keyword within the loop to tell the program when to stop executing the loop. Recall that we did this in the guessing game in the quitting after a correct guess section of Chapter 2 to exit the program when the user won the game by guessing the correct number. Now, we also use continue in the guessing game, which in a loop tells the program to skip over anything remaining in the code in this iteration of the loop and go to the next iteration. I assume it's going to show us some examples. Oh, it's maybe not? We'll see. We'll keep going. So returning values. I think I was mentioning this. You can actually assign values to a loop, which might hurt some people's brains if you're used to other programming languages that don't, but this is, I think, one of the things that is pretty idiomatic for using Rust is that you don't always have to or even want to write something out as a separate function just so you can go, you know, like let x equal foo of blah, blah, blah. Sometimes it's, I wouldn't say simpler, but more in place, more locality of behavior to just go, I want to write out the instructions to make this variable right where I'm going to have it defined as a variable. Does that make sense? Write out the instructions to make the variable right where I want to define it or something like that. Anyway, so let's go mute counter. Let mute counter. We're making a mutable variable. We can change it, and we're going to bind it to the value of 0. And then we're going to take our loop and go let result, which is also basically saying whatever is on the left hand, whatever is on the right hand side of this assignment becomes the value that gets stored in result. And we'll put a semicolon there because we're going to give back a value. Here, if I'm not mistaken, we will get to the actual example that they show, but I'm just going to, you know, indulge my curiosity for a sec. I think this should be the unit type that is returned by the printline macro, or the function or whatever is calculated that results from using it anyway. Let's see if my speculation is right. I don't know the answer. I'm actually just apparently reusing the same code. Hang on. Something weird happened there. Because that definitely wasn't the program. Oh, no, it's probably the right program, but there just isn't a break condition. Yeah. So let's, I'm curious if this is the right, yeah, okay. It's the unit type. The unit type is that open close parenthesis. This code will break. It won't actually run correctly. Okay, so enough of indulging my curiosity. You probably don't know and don't care about whether that returns a unit type at the moment. We've got let result be bound to whatever this loop evaluates to. So we'll follow their example and go, what is this loop going to do? We're going to increment counter, which is fine. And then we'll say if counter is exactly equal to the value of 10, then we will break. And break inside of this loop is also, it's not just acting as a, hey, stop the loop here, although it is doing that. It's also acting like a return statement and saying this is going to become what is given to result. Okay, am I missing anything else from their example? It doesn't look like it, so let's go ahead with running this example. So the result is 20. Why? Because this thing starts at 0, and it counts every time it loops until you get to a count of 10, and then you break out with counter times 2. But if it's 10 and 10 times 2 is 20, then that's the value of result, and therefore that's the value that gets printed in this print statement below. Okay, enough of that. Before the loop, we declare a variable named counter and initialize it to 0. Then we declare a variable named result to hold the value returned from the loop. On every iteration of the loop, we add 1 to the counter variable and then check whether the counter is equal to 10. When it is, we use the break keyword with the value counter times 2. After the loop, we use a semicolon to end the statement that assigns the value to result. Finally, we print the value in result, which in this case is 20. You can also return from inside of a loop. While break only exits the current loop, return always exits the current function. So in this context, that would actually be our main function, which you probably don't want to do. I'm not saying there's never a use case for it, but I don't think we're at the stage where it makes sense to try doing that. But what they're saying is, like, for example, if this got all the way to the end, I mean, you could return out, I don't know. I'm not sure if we can do unit type. Apparently it's valid rust. Basically, it would return no error or any result or anything like that. Mind you, you should be able to also do that right inside of the main function here too. And that should actually execute. So yeah, it's not just that it's unreachable. That is valid. We are returning the unit type when we do that instead of, I guess, like a result or something like that. Okay, we'll learn more about results and return types for the main function, I'm sure, later on. Disambiguating with loop labels. If you have loops within loops, sounds pretty loopy to me, break and continue apply to the innermost loop at that point. You can optionally specify a loop label on a loop that you can then use with break or continue to specify that those keywords apply to the labeled loop instead of the innermost loop. So by default, break and continue are things that will affect the inner loop behavior. But if it's with a special label, you can kind of name the loop and then refer to it by name. So loop labels must begin with a single quote. Here's an example with 2 nested loops. Let's do it. So the first thing that we've got going on here is we'll create a mutable variable u32 integer called count. And here we're going to write this label. What is it? A quote, single quote, counting up. And that's basically a name of this loop. So inside of that, we'll go print line macro, and we might say something like our count is equal to the actual value of count. It's a good start, but let's keep going. Let mute remaining be bound to the value of 10. We do this every time we iterate this loop, this outer loop. And then we'll go inner loop, a loop inside of a loop. We're going to get real loopy here. So print line macro, and we've got remaining is bound to the value of whatever the actual variable remaining is, whatever it happens to be. If remaining is exactly equal to 9, then we will break. And this break is just breaking out of this inner loop. It's not breaking out of the outer loop. Okay? So we can break, and then we can also say if count is exactly equal to 2, then we might say break counting up. Now this will break out of this outer loop. Okay? Now, the next step that they want to do here, and keep in mind there's basically two state variables that we're playing around with here. One of them is this remaining, which is a countdown from 10, and I'm saying it's a countdown because we go minus equals 1 to decrement it. And then we've got this outer count. And so it's two different pieces of state to keep track of here. That's all that I mean to say. So we got count, and we will increment count by 1 for every iteration of the outer loop. And then lastly, just for the sake of printing some stuff, the end count will be bound to the value of the variable. Not bound to, sorry, this is not in the actual Rust, this is just in the string. But we're going to display it as end count equals the value of count. Okay, I think we've typed out their example correctly, and if not, we'll find out. So we get this kind of history that plays out. First, the count starts at 0, and the remaining number starts at 10. But then we've got this minus 1 that results in that being 9. And we also have the count goes up to 1 because we have this plus 1 count. And then we go, notice that for every iteration of the outer loop, you have some number of iterations of the inner loop, right? So we see this remaining at 10 again because inside we're reassigning that whatever remaining was, it's now back to 10. And then it goes to 9. And then it goes, we increment count again. That's this this plus equals 1 again. And then we're at the top of the loop, the outer loop again. And so we reset remaining to 10. And then we print end count is 2, because when we finally get to remaining is, if count is equal to 2, then we break out of this outer loop. So in the first round of that going through the outer loop, remaining equaled 9, so we broke out of the inner loop, but we just went straight to count plus equals 1. We did not break out of counting up. Does that make sense? If this doesn't make sense, it's worth playing around with it yourself until you understand this idea of breaking out of inner versus outer loops, and really watch what's happening with count, with remaining and count in these print outputs. They explain a lot. Okay, so the outer loop has the label counting up, and it will count up from 0 to 2. The inner loop, without a label, counts down from 10 to 9. The first break that doesn't specify a label will exit the inner loop only. That's this if remaining is equal to the value of 9, then just break. The break counting up statement will exit the outer loop, and that prints this, and we talked through that. So anyway, that's an example of using an inner loop to use and a label to break out of the outer loop from within the inner loop. Otherwise, you can do some like flags where you keep track of, have you broken out of the inner loop in such a way that you should also break out of the outer loop. You can do it, but it gets even more complicated if you have like if you have like 3 loops nested in. So anyway. It's just to make your life a bit easier for syntax, I believe. Streamlining the conditional loops with while. A program will often need to evaluate a condition within a loop. While the condition is true, the loop runs. When the condition ceases to be true, the program calls break, stopping the loop. It's possible to implement the behavior like this using a combination of loop, if, else, and break. You could try that now in a program if you'd like. I think we'll skip unless it's part of the actual examples they want to show. But feel free to do that, or leave a comment if you go, no, Galen, I really want you to see, I really want to see you do this. Then we can do it. However, this pattern is so common that Rust has a built-in language construct for it called a while loop. Thank goodness. And thank goodness it's not a go-to statement. Okay, in listing 3-3, we use while to loop the program 3 times, counting down each time, and then, after the loop, to print a message and exit. So let's copy out their example. I like to run stuff for myself. I don't know if you've noticed this. I mean, you can click on these little play buttons that will run the code, but I just feel like it's good for my brain to type it out. So we're going to bind let mute number is bound to 3. And then we'll go while number does not equal 0. We'll do some stuff. We'll go maybe print line macro, and we'll print the value of number. And then we'll go number minus equals, example says 1. So we'll do that. And then we'll go print line macro, left off, because we're pretending that we're doing something as awesome as rocket science, I guess. I don't know. It's a pretty straightforward program. So to quickly explain, this is some initial state, right? We got while number is equal to 3, number is equal to 3 as its initial value, and it's mutable, so we can change it. And while number is not equal to 0, do some things, right? So first we're going to print the number just to show what it is, and then we're going to decrement it. But if you think about it, if you start at 3, and then you go -1, and then you go back to the top, and you print, and then you go -1, and you do that another time, eventually you get to 0, right? So what we should expect is for it to be a countdown, just like the liftoff print line macro suggests. And there we go, 3, 2, 1, liftoff. Does anybody feel like a rocket scientist? I don't. Okay, so that's nice. Using a while loop to run code while a condition evaluates to true. This construct eliminates a lot of nesting that would be necessary if you used loop, if, else, and break, and it's clearer. So even in Rust, sometimes we care about readability, but usually with less compromise for performance than maybe some other programming languages. While a condition evaluates to true, the code runs. Otherwise, it exits the loop. Now, looping through a collection with for. So we mentioned there's 3 different types of loops, right? There's the loop, the one that's just called keyword loop. We just saw while loops, and now we're going to get into for loops, which are like kind of the bread and butter of almost every programming language, I guess. You can choose to use while construct to loop over the elements of a collection, such as an array. For example, the loop in listing 3-4 prints each element in the array called A. Let's type out their example. You know I'm a big fan of typing out the examples. So let A be bound to the value of, we've got 10, we've got 20, we got 30, we got 40, not that old yet, and then we've got 50, sorry. And then we're going to also say let mute index. Note that our list A here is not mutable, but our index is. All right, so we're going to go while index. Okay, so this is not a for loop. They're showing us that with a while loop, you can go over a collection. But I think what they're going to show us in a moment is, well, for loops are an even nicer syntax for when you can kind of say ahead of time what the set of elements are that you need to loop over. So we got while index is strictly less than 5. We'll do print line macro. And we'll say the value is blah, blah, blah. A at the index for whatever iteration index is. And of course, we're missing something because otherwise index would stay at 0. We need to update index. So we'll go plus equals 1 to update the value of index. Remember, index is mutable. So then we can go cargo 1 and we can see, well, the value is 10, and then it was 20, and then it was 30, and then it was 40, and then it was 50. Fair enough. It's a way of going through the elements of an array. Here, the code counts up through the elements in the array. It starts at index 0 and then loops until it reaches the final index in the array. That is, when the index is strictly less than 5, when the condition, index is strictly less than 5, is no longer true. So running this code will print every element in the array like this. That's what we saw over here. Now, all 5 array values appear in the terminal as expected. Sure. Even though index will reach a value of 5 at some point, the loop stops executing before trying to fetch a 6th value of the array. Now that is kind of interesting. Like, we didn't include any kind of breakpoint. Instead, Rust has done something kind of smart of knowing that basically at compile time, looking back and going, well, A only has 5 elements, and like this code could only possibly go so far. So unlike some of the other code we saw before, where it would just keep printing like again and again and again and again, that it actually does stop, because the Rust compiler is smart that way. However, this approach is error prone. We could cause the program to panic if the index value or test condition is incorrect. Right, so it happened to be the case. Oh, I messed that up. Sorry, folks. Completely messed that up. The reason why we stop at 5 is actually because of the condition, not because Rust is smart. That was my bad. So, however, this approach is error prone. We could cause the program to panic if the index value or test condition is incorrect. For example, if you changed the definition of the A array to have 4 elements, but forgot to update the code to while index is strictly less than 4, the code would panic. It's also slow because the compiler adds runtime code to perform the conditional check of whether the index is within bounds of the array on every iteration through the loop. So that's kind of an interesting point, that for loops, which is what we're getting to, although they haven't said that yet, are going to have this kind of optimization that while loops don't, because while loops are in some sense more general. For loops are more specialized to going, well, there is some bounded collection that we're gonna iterate through. So as a more concise alternative, you can use a for loop and execute some code for each item in a collection A. For loop looks like, a for loop looks like the code in listing 3-5. Let's look at their example. So they have the same array A, but we drop out the index variable, don't need it, and we can basically say for element in A. This to me looks like a lot of high-level programming languages like Python, and I'm sure Ruby looks similar, where you just go like, I just have this collection and it's a bounded collection in terms of its number of elements. So, and it's defined ahead of time, so why don't I just say for each element? It's great. It's a very simple syntax. And you don't need those bound checks on the arrays at runtime, which saves you some compute. So this is one of the things that can be more efficient sometimes about using a for loop. I forgot to close the string. That's why it's yelling at me. There we go. And there's our very similar, identical really, output, but implemented differently. Great. So when we run this code, we will see the same output as the previous listing. More importantly, we've now increased the safety of the code and eliminated the chances of bugs that might result from going beyond the end of the array or not going far enough and missing some elements. Machine code generated from for loops can be more efficient as well because the index doesn't need to be compared to the length of the array at each iteration. That also makes sense. We completely got rid of the index variable, and that there's some internal stuff that is presumably optimized for this type of task. So using the for loop, you wouldn't need to remember to change any other code if you change the number of values in the array, as you would with the method that we listed with the while loop. So the safety and conciseness of for loops makes them the most commonly used loop construct in Rust, and I think many other programming languages, because it's very compute efficient. And very syntactically nice to go, I just got a collection of things. I just want to say, do something for each thing. Even in situations in which you want to run some code a certain number of times, as in the countdown example that used a while loop in the listing a couple of listings ago, most Rustaceans would use a for loop. The way to do that would be to use range, provided by the standard library in Rust, which generates all numbers in a sequence starting from one number and ending before another number. Here's what the countdown would look like using a for loop and another method we've not talked about, the rev, to reverse the range. Great. So we're gonna get rid of all that, and say for number in this thing that looks like a tuple, but is not a tuple. As far as I know, does Rust LSP give us anything? No information available. There we go, an ops range, a half open range bounded inclusively below and exclusively above. So that's one thing to keep in mind from a math point of view of how many iterations you expect to occur and up to what actual value number will actually take. So we've got reverse, which means that instead of going 1, 2, 3, it's instead going, 1, 2, 3, it's going to go 3, 2, 1. That's my prediction, if I remember the right way to do the counting. So we'll go print line macro, and we will throw in number, exclamation point just for flavor, I guess. Add a little bit of salt and pepper and number into it, and exclamation. And there we'll put lift off. So 3, 2, 1. So my prediction was wrong because I forgot that there was a exclamation point, but otherwise it's 3, 2, 1. So that's fine. This code is a bit nicer, isn't it? I mean, they didn't show us like the worst case, of course. The worst case probably would have been to implement all of this stuff ourselves with like a while loop or whatever. Maybe it's not the worst thing, but it's what they were alluding to is the thing that was more work. So we're finally at the summary. We are just about done talking about the control flow section for the common programming concepts in Rust. And in fact, this is the last section for the common programming concepts. And the next section will be understanding ownership. So we'll finish up by reading their summary. You made it. This was a sizable chapter. You learned about variables, scalar and compound data types, functions, comments, if expressions, and loops. To practice with the concepts discussed in this chapter, try building programs to do the following. We won't do it in this video, but maybe I'll insert some additional videos as we go along to do these exercises, just because I need a break from talking. So try building programs to do the following. Convert temperatures between Fahrenheit and Celsius. This is a classic computer programming problem. Generate the fifth Fibonacci number, which is kind of like an additive recursive relation, very popular in math, and print the lyrics to the Christmas Carol, the 12 Days of Christmas, taking advantage of the repetition in the song. That's a little bit vague. There might be multiple ways to do that one. We'll see what I decide to do. But anyway, when you are ready to move on, we'll talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership. And I think that's going to be a huge deal because, because it's not in most other programming languages, even if you are not new to computer programming, but you are new to Rust, you are not likely to have dealt with ownership. Although from what I've heard in passing, not an expert in what programming languages support ownership, but I've heard that other programming languages do actually have some kind of support for this now. Anyway, thank you for watching and enjoy the rest of your day. Take care. Bye.